So in this video, we're going to finally solve an exam question on forces and statics. Great. We're going to bring all the ideas from the previous videos together. So hopefully you've watched on the really what the force is and you've seen how to resolve forces from the previous 4 videos. There's one more idea that we need to know about before we can actually solve this question. And that's just what this word equilibrium here means. So if forces are in equilibrium, if Pascal's in equilibrium, it just means that the sum of forces, that thing we calculated in the last video, that is equal to 0, 0. There's no overall effect on the forces are balanced, you might say. The forces towards the left and right cancelling out, the forces going up and down are cancelling out. We'll talk more about this when we get there, but that's the last bit of information we need. Let's read through the question and try to do all the jobs we've learned how to do. A particle of weight 8 newtons is attached at C to the ends of 2 light inaccessible strings AC and BC. So I'm thinking really what the force is. It's mentioned weight, so let's get the weight force on there. The weight here is 8 newtons. So let's draw downwards weight here of 8 newtons. That figure 1's just a little bit in the way, isn't it? The other ends, A and B, are attached to a fixed horizontal ceiling. Yeah, I can see that. The ceiling hangs in rest in equilibrium. That's important for later. With the strings in a vertical plane, that just means that the whole thing's in a sort of 3D, like a 2D plane, rather than it being like in and out of the paper. It's just looking as it looks on the paper, so don't worry too much about that. A string AC is inclined to 35 degrees. Yeah, I see that in the question. And the other string BC is inclined to 25 degrees to horizontal. Yeah, I see that. Find the tension in string AC and tension in string BC. Yeah, there are tensions because it's a string, so let's add those tensions in. So tension going this way and tension going this way. They are different sizes. There's no reason they should be the same. 2 different strings. Let's call them T1 and T2. We don't care about the forces at A or B because that's not the particle of interest. We care about the forces on C and the resultant force on C. So there's no reaction or friction here because C isn't touching a surface. It's not on a surface. It's not rubbing against a surface. So it's going to have no reaction, no friction. So we've got the forces. First job's done. Second job is going to be to actually add on our axis. So let's do it in a different colour. I'm going to draw the axes going the way you might expect. X going this way and Y going this way. It's best to mark them all, I find, so you can see the angles you're looking for more easily. Because now we want to add the angles. So this 8 Newton force, this is going straight down. This is quite an easy one to resolve. We can probably just write down that vector straight away. But this T2 and T1, we need the angles that I gave to you in the last questions we're doing. And that's going to be to do these 25 and this 35, right? So hopefully we can see this 25 degrees is forming this kind of Z angle, this alternating angle. And so this angle here is going to be also 25 degrees. It's the angle between the string and the horizontal ceiling is the same as the angle between the string and this horizontal x-axis. These two lines, x and the ceiling being, of course, parallel to each other. And similarly over here, we've got another alternating angle, another Z angle. So this is also going to be 35 degrees. With those angles, resolving these forces should be fairly easy, right? Did it last time. This 8 newtons, let's get out of the way first of all. It's going straight down, so no x. It's going down, so 8 in the y, and it's negative because it's going down. The T2 force here next, perhaps. This is making an angle to the x-axis. So we know it's going to be T2 cos in the x and T2 sine in the y. Sorry, let's write it down properly. Cos here and sine here. And the T1 similarly is going to be making it to the x-axis. It'll be T1 cos on the x part, sine the y part. Think about angles. So I think about the actual minus signs, which way it's going. So this T2 is going positive in the x part and positive in the y part. It's going both to the left and going up. Sorry, to the right and going up. So it's positive, positive. But T1 is having a negative part. So T1 is going to be negative here in the x part because it's on the negative x-axis, but positive in the y-axis. It's going to the left and going up, right? I think that looks okay now. We've got all the forces, so we can say now that the resultant force is equal to 0, 0 because it's in equilibrium. We can write down the resultant force. That's the sum of all forces. So minus T1 cos 35, T1 sine 35, plus T2 cos 25, and then T2 sine 25. And then we've got here a 0 and a minus 8. And that's equal to 0, 0. And then finally, we can do the fact that if you've got a vector equal to a vector, that the x part equals the x part and the y part equals the y part. So we could write this down as just two separate equations. We could write down as being minus t1 cos 35 plus t2 cos 25. And we probably get rid of that plus 0, right? That's not really very important. Well, that's being equal to 0. And then we can write down t1 sine 35 plus t2 sine 25 minus 8 is equal to 0. And believe it or not, out of these 8 marks, we've probably got about 6 of them. These equations, they're fully correct, are probably about worth 3 each, 2 or 3, something like that. And actually, to solve now to find the two unknowns, t1 and then t2, isn't that difficult, but now it's a pure maths problem rather than a mechanics problem, right? And for now, we're going to solve these later. We'll learn how to solve these soon. But for now, let's just try and do another question and see if we can do the same jobs. The jobs were to do really what the forces that the force is on, and then to add on those axes, and then to work out the angles, resolve the forces, and then write down finally that the sum of forces is equal to 0, 0. So let's try that again on another question. So let's have a look at this one. A particle P of weight W newtons. Let's get that W in there. So this particle P is going to weight straight down. Is attached to one end of a light elastic string. Yeah, I can see it. The other end is attached to a fixed point O. Yeah, so PO here is the string. A horizontal force of magnitude 5 newtons applied to P. Okay, so this 5 newtons has come from somewhere. Who knows where really? This is just some force that is already there. And the particle P is in equilibrium with the string taut, and with OP, the string, making an angle of 25 degrees to the downward vertical. Yeah, I can see that angle there, as shown in figure 1. Okay, so it's in equilibrium, so we know that the resultant force here is going to be 0, 0 again. We can use that later on. So we've really got to add the forces, right? So we've got the weight on. Do we need a reaction force? No, because the particle P is not touching a surface. No friction then because it's not touching a surface. So just this tension force from the string going along the string away from the object. There's 3 forces here though, because the 5 Newton force they already added for us. So there will be sometimes forces that are on the diagrams that we haven't got to worry about. This is just for forces that we might have to add on ourselves, right? Next job, add the axis. Let's switch color. So I put an axis for x going across this way, an axis for y going this way. We won't always have the x and y axis going horizontal and vertical. We'll see planes and slopes and stuff later on when we'll incline the axes, but for now we're going to draw them on like this. And then we're pretty happy with trying to resolve the forces for W, and for 5, we could perhaps just write this down. W is going to be 0 and then minus W, right, because it's going down the y-axis. And then here we're going to have a minus 5 and a 0 because it's going along the x-axis but going towards the left. This T, we need to work out the angle. So this 25 degrees, we can either go this kind of Z angle again because it's vertical and vertical, or perhaps there's other ways of looking at it as well, but we'll put a 25 there. I guess we could work out this angle here by using the 90-degree triangle and get 65. I think either would work for us. Let's just put that 25 in there right now. And then we can resolve that one. So this time we're going to have T and T. This time the cos is going to be to the y axis, right? We have the T to the y axis. So we're going to do T cos 25 to the y axis and then sine 25 there. The triangle we're used to is like slightly rotated, right? It's like here's the angle, here's 1, so there's the cos on the y-axis. So that gives us our forces. I think the T is positive, positive here because it's a positive x part and the positive y part. That looks good. So now we can use this resultant force idea. And we can add all the forces together. We can do T sine 25 and then T cos 25, and we do minus 5 and 0, and then 0 minus W, don't miss a force out, and that's equal to 0, 0 because the forces are balanced. Go right down here, T sine 25 minus 5 equals 0, because top part equals top part, and t cos 25 minus w equals 0, because the y part equals the y part. Notice here that you've got sort of two equations, and it makes sense, right? We've got t sine 25, and that's going upwards. So that's going towards the right, this is a right force, yeah? And then you've got minus 5, which is going towards the left. And those two forces are balancing out. So we've got positive and negative giving 0. That makes sense. We've also got a t cos 25, which is going up, and a w, which is going down, and that's cancelling out. If, say, I made a C mistake and I'd put a plus w here by mistake, hopefully now I'd realise that two positive numbers can't add to give 0, and I would fix that and go, oh yeah, God, I missed the minus sign of the w. And now we can try and solve these. In fact, solving these is not very difficult at all, so I leave it an exercise for you guys to work out, and I'll put the answers down in the description so you can check and see if you were right. I'm sure maybe there'll be some comments of correct answers in there as well. That's all for this video. We'll look at some more complicated problems on slopes next. Good luck, hope it was useful, and see you in the next video.